Hello, everyone, and welcome to another Stark at Home. My usual first question, can you see and hear us? You can type in the chat. Yes, thank you, Martinez. Okay, so thank you everyone for joining. We do this crowdcast or webinar from time to time. It's been going on for more than a year, and we use it to discuss serious math and engineering in an informal and intuitive setting. And this time we'll be discussing polynomial commitment schemes. So to tease the audience in social media, the way we posted it is we'll have the big KZG versus FRI fight or debate. These are different ways to commit to functions that happen to be low-degree polynomials over finite fields. For those who feel already a bit lost with the notation or with just the words polynomial, this will be a discussion of math, cryptography, and engineering. So if you don't know what a finite field is and what a polynomial is, then it's probably going to be hard for you to follow what will go on. How shall I say it informally for those of you who don't know what polynomials are? These are
1 plus x square.
Yeah, but I wanted to say these are succinct mathematical expressions that the nice thing about them is that you can very efficiently calculate them. So the canonical example maybe would be a parabola equation, y equals x squared plus 5x. And that's an example of a polynomial. So the nice thing is that even you have this short formula and you can evaluate it at many different places. So the nature of the beast we're discussing today are ways to commit in an irrevocable way to a polynomial, to such a mathematical expression, so that later on you will answer consistently with that expression. And we will be discussing it not in the context of high school algebra, which usually is over the real numbers. We will be discussing it over a mathematical world called the finite field, which you could approximate as whole numbers modulo some fixed prime. That would be a good approximation. And the reason we care about these things is that it turns out that all existing SNARKs and STARKs and commit and ZK systems implemented out there in the end require such creatures. And there are quite a few different ways to commit to polynomials. The title mentions 2 of them. There are many, many more. And in particular, we'll be introduced to another one here today. So on this, maybe we'll do a quick round of introductions. I'm Eli from StarkWare.
I'm Shahar from StarkWare also.
I'm Jim from Ulvetanna. We're making hardware-accelerated high-performance SNARK proving clusters.
Hey, I'm Zach from Aztec. We are a privacy-focused L2 rollup on Ethereum.
I'm Mamy from Taiko. We're a layer 2, not yet in mainnet, soon, and we try to be the most compatible with Ethereum, according to Vitalik, as a type 1 ZK EVM.
So the way we'll go about it is we'll present in sequence these different commitment schemes and argue in favor or against them. And from time to time, we'll pause to answer questions. I just wrote a sample question. Please use the question button to submit a question, because otherwise through the chat, it will be very hard to to answer. So without further ado, I will try and share my screen and start. We'll start with FRI, move on to KZG, and end with Binius, 3 different commitment schemes over different fields, and discuss the merits of each of them. So I will try and share my screen now again. Okay. So what I have here is a presentation that I'll be doing jointly with Shahar, or rather, he'll do most of the work. It is based, so as I said, this is a place for informally discussing serious stuff, but under the guise of informality, I took here slides that I haven't touched since August 2023, when I presented something like this at the Stanford Blockchain Conference. So some of these things are not exactly quite updated. But back in the day in August 2023, if you looked at many of the blockchain projects that use zero-knowledge proofs and deploy in practice, they roughly use 3 different kinds of polynomial commitment schemes: FRI, inner product arguments, and KZGs based on pairings. And I'm sure the picture has changed since then, but I haven't had time to update this. But definitely these 3 are prevailing, and I would say that between FRI and KZG, a lot of projects are using, less so with inner product arguments, but there are a few. So I won't discuss, or we won't discuss too much inner product argument, at least not on our side. So I will hand it over to Shahar, please.
Yes, thank you. Maybe I'll share it on my screen.
Okay, I will stop sharing. How do I do that?
Okay. Sure.
Yes, we can see.
Okay. Try to do the slideshow. Yeah. Okay. So first of all, okay, this is based on Eli's presentation from a few months ago. I tried incorporating all the optimizations people told me online about KZG, but the truth is that I don't know enough about KZG implementation, so I'll leave most of it to the other experts here. I'll try to focus on FRI. Well, the first at the existing implementations, and for FRI we have the Stone prover that we open sourced a while ago, and I tried to estimate the clock cycles it takes per word. Now the measurements I'm using how many clock cycles to commit on a word of about 32 bits in a stream of about 2 to the 20 words, about 1 million words. So there's some computation here. If I don't want to dive into exactly what everything is, but it's based on concrete estimations of clock cycles from existing code. And for Stone today, using a big field, this is about the number of clock cycles. Now, for existing solutions to KZG, I'm not aware exactly what there is or isn't, but I'll try to compare it to something maybe theoretical. So here I'm looking at an ideal implementation of FRI versus ideal implementation of KZG. That's because I don't know what actually exists on KZG. So on KZG, if I understand correctly, you need a big field, and this has this overhead of using a big field. And for FRI, I'm trying to use the new approaches taken by other people like Zero, and also we are also working on small field provers, which yields these numbers. Okay, most of them are really estimations. So again, KZG guys will probably have better things to say here. But on the FRI side, looking at the ideal non-vectorized implementation I could come up with is using a Blake 2 hash, which is like a very fast hash that we can practically use and do use in Stone Prover. We're using a small blow-up factor, so it's a trade-off between prover and verifier, but in a lot of cases it does pay off. And I'm using a field like a 32-bit field, which is used today in things like risk zero, and got this kind of estimation. Now this looks, KZG and FRI here are very comparable, I'd say, in the ideal non-vectorized version. FRI looks to be a bit better, but again, maybe KZG people will correct me. Now, when you go to vectorized, I'm not sure how well KZG is getting vectorized, especially with using this figure on the number of multiplications needed for a group operation. If I recall correctly, this is Zach told me that it can be done using 6 multiplications. I'm not exactly familiar with the algorithm or how much overhead it has, or if it's easily vectorizable. So this is unknown for me here. I do know that the FRI is like very vectorizable, and everything scales almost linearly with how much you vectorize. From benchmarks we did as well. So FRI is easily vectorizable. You can see that it takes a small number of clock cycles. And yeah, this is just theoretically comparing a number of operations. This is like more less practical, less counting clock cycles, more just raw operations. And you can see there is like a trade-off FRI that uses a lot less group operations and pays with hash operations. So it does make sense to use maybe quick hashes, and this is, I'd say, where the trade-off comes from using hashes over group operations or field operations. And other considerations is, I'd say, one benefit of FFT is it's a bit more structured, the algorithm itself, and uniform than the MSM one, which needs to divide things to buckets. On the other hand, the memory access pattern of the FFT is a lot harder. On MSM, you just do a linear pass on all the data, but in FFT, you have these wide strides, sometimes transposes. So this is like pros and cons for each one. And just last thing, it's about whether we are memory bound on FFT or all of these. So the answer is probably sometimes it is memory bound, sometimes it isn't. It depends a lot on the architecture. I took here for a thought experiment, what if we ran it on like an A100 GPU, just because it really has a very good memory bandwidth. So it fits for the FFT use case. So for the GPU A100, that probably fits very much on the GPU, on the FRI and FFT use case. I did some back of the envelope computations here. It doesn't matter at all, but it seems like it shouldn't be memory bandwidth, or maybe very, very close to being memory bandwidth. So in this case, it fits very well. And thus the number of instructions is very important. Okay, this is what I had to share.
Can you go back maybe to the to the slides with the very first comparison? I have a few comments. I assume Zach also had some, because in August there was this Twitter debate following those slides.
Yes, there was, and I was trying to incorporate all the.
Can you go back in the slides with the let's go there. So the first thing is currently the comparison is committing to a word, but because KZG uses big field, whether we commit 32-bit or 256, it's the same cost. So if you go one slide later, and again, you see the total is 20 million and 154 million with back of the envelope. But if you multiply it by 8, so if you want to commit to 8 words with FRI, we go to 160 million. So with just back of the envelope computation, we're in the same range.
I mean, I maybe I got it wrong, but I did try to account for it already. That's why on the right there is like W over log n, no, W bits, but over log n because of the buckets. And on the left,
no, I mean the word size for KZG is 256. It's not 32.
I did assume here that you know we are committing on a total of 2 to the 20 times 32 bits overall. That is the computation I did. Does it not make sense? Did I do something wrong here?
I mean, this brings up this idea of what are we committing to, which I mean I'm going to talk about later, but essentially in arithmetization, sometimes you want to commit to 1-bit values or 8-bit values or 32-bit values, even though your field is much larger. So I think what the KZG folks are trying to point out is that if you have like an information dense trace where all of the committed elements actually have 256 bits of useful information, then this comparison doesn't compensate for that. Is that accurate?
Yeah. Why doesn't it compensate for it? I'm not sure why, because if you have twice the number of bits, then the right one will cost twice more, and the left one will also cost twice more, but assuming that you can arithmetize it in a similar way. Like if I had 250 bit words, then on the right, okay, it would be 4 times the cost here.
No, it would be the same costs, because in your costs you
why? I mean, your bucket size is like log n.
Log n, log wn, but it's about the same. So log n.
Yeah, I agree with Shahar here that because the more or less right, like the cost of your scalar multiplication in KZG is going to scale linearly with the number of bits of information that you're committing to, and so here Shahar's chosen 32 bits of information to commit to.
Okay.
So if you scale to 256 bits, then you'd have to multiply the KZG cost by 8.
Yeah, and a good comment that I did get here is that I'm assuming that all the arithmetizations are optimal. So I'm just considering committing on raw bits, on the same raw bits, which is it maybe doesn't fit for every arithmetization. That is true. But
I think what would happen is if you multiply by 8 the word size and you divide by 8 the number of words, right, which is like making it 256. Assuming that you need to multiply by 8 or whatever, maybe it's by 4 to get from 32 to 256. I think it's a factor 8. Then the cost would now become, if you look at the cost formula, it would be a little bit worse, because it would be 256 divided by 17.
On the right, you mean?
Yes, on the right.
On the right, it's actually W over log WN. So I just neglected it. But the overall cost is actually just WN.
No, we agree. I was thinking in terms of 2 to the power of 20 in terms of number of points, because that's how we usually benchmark on the KZG side. If you do this with W, that's okay. Which brings me to the other point. So if you look at the cost formula, FRI, FFT scales as n log n, while KZG scales at n divided by log n. So that's one of the big research in the past 2 years was in Hyperplonk, Hypernova to remove FFT and make sure that we only have MSM due to these asymptotic costs that are better than FFT.
Mm-hmm. Yeah, it makes sense. Though, do keep in mind that these FFTs were FFTs on large fields. We did have large constant to them. I agree that asymptotically the right one is better than the left one, but I think that practically in the cases that we looked at, it seems that FRI is better by constant. For example, in these cases. But yeah, the KZG is asymptotically better. That's true. Okay. Any other questions? No. Right.
Well, maybe the audience has questions, and again, please use the the ask a question button.
Yeah, I see that Ariel asked if 2 to the 20 is large enough for good comparisons. I think that practically it is a size that we would want to use, 20 or maybe 24, which is quite similar. These are sizes that we want to use. It's it's enough, like millions of operations. Considering that you are doing recursion afterwards, then it's mostly enough.
I wonder, like, what other, memory or other effects would come as you, or maybe, is it something, because 2 to the 20 is just some constant, like, why is it the sweet spot, or why do you think it's the sweet spot?
I mean, another thing on KZG is that in order to get the n over log n scaling, you need to increase the number of buckets, which is part of the Pippinger's algorithm, which is a large memory requirement. So in practice, KZG and MSM implementations are often limited by how much memory you can allocate for buckets.
Can I actually dispute that? That's not my experience at all. That generally the memory cost for your buckets is going to be, it's going to be roughly log n. That's approximately the number of buckets you're going to have, which is a trivial memory cost compared to the actual information you're committing to.
I think log n is the bucket size. Don't you need n buckets?
No.
No.
You basically, the way Pippinger's algorithm works is you iterate over your points, and depending on the size of your scalar multipliers, the values, you assign that point into one of a number of buckets. And generally, the sweet spot is the number of buckets is going to be the log of the number of points you have to multiply. And given that each bucket is a point, it's a pretty trivial memory cost.
It really depends what you need to have in memory. So I look at it from our experiences doing hardware acceleration, where you don't need the scalars to be in memory. They're being streamed into a device and then do not need to be retained there, whereas the buckets do need to be stored in some local memory where you're constantly updating them. So you can scale the size of the MSM far more easily by streaming in more data, but you would, in our experience, be limited on.
I see. Yeah, so it's not. Yeah, we're not talking apples to apples here, because the context that I focus on is client-side browser proving, where everything is CPU based and where those constraints don't apply.
So I have some, let's see, some table there to share on the bucket. So this is coming from my own library. To be comparable, we need to divide by 8 because this is using 256 bits. So around this, and the number of buckets that we have is 2 to the power of 14. So the size is 16,000 multiplied by 32 bytes. So it's very small in terms of memory, and usually the memory issues in Plonk-based prover is actually the FFT that are very big. Another thing is that usually for Planck, at least when working at Taiko, the size, the number of points that we are looking to commit to is around 2 to the power of 24 to 26. Yeah, and the maximum for Ephraim is 2 to the power of 28 because the curve has this limitation.
Excuse me, the maximum of what? Which curve has limitation?
The 2 adicity, so of BN254 is 2 to the power is 28. So we cannot. So this is actually a limitations on the FFT side. To do an efficient FFT, we have to be below 2 to the power of 28. Anyway, but yeah, the number of points that we're interested in is often 2 to the power of 24 to 26.
And wait, the number of buckets is what you have in the 4th column?
There. This is the number of buckets. So
okay, so the number of buckets is it's not log. It's roughly the same number as.
But it's like a square root or something. You don't need it n. It is.
So
like,
yeah, if you go by those like the raw algorithm and the asymptotic physics, it should be log. But then
you have a YouTube link that goes there, but I compute the number of buckets depending on the number of operations to minimize the number of addition and doublings everywhere. And there is this, I'll post it in the chat by Gus Gutowski, I think, from a ZK Study Club link that goes over the exact details to minimize the number of operations. And yeah, it's roughly log of the number of points. Yeah.
Okay. Who wants to go next? So we tried to present the case, I think, for FRI, but yeah.
Why don't I start on the KZG side, then maybe you could follow up, because I think we have two very different perspectives because of the different applications and use cases that we use KZG for. One thing I do just want to highlight from what Mamy said was that the new Planck iterations, hyperplonk, things like that, the fact they don't require FFTs is an enormous boon, which crushes down memory consumption. And it also makes the entire algorithm much more parallelizable, not just within a single device, but across multiple physical devices, because the amount of memory shared that needs to be shared is substantially smaller. So this is something I have direct experience with, but I imagine that it's a lot more practical to have enormous circuits, 2 to the 30, proved over giant compute clusters. If one uses KZG combined with a sum-check-based hyperplonk style scheme. But yeah, going back to, okay, so you've got a SNARK, you've got some application, you want to build some ZK stuff, some ZK tech, and you've got to pick a polynomial commitment scheme. What are you going to do? Well, I think a lot of it is is very much focused around the execution environments and the architecture of your overall of the higher level system you're building. So let's take Aztec, for example, and why Aztec uses KZG. We are a privacy-focused LT. What does that mean? It means that we're actually using the zero-knowledge property of ZK SNARKs, and that transactions to our network can be end-to-end encrypted. Our state databases are encrypted. Transactions are a list of encrypted state changes to be made, plus proof of correctness that the rules of the network have been followed. And those rules are encoded in smart contracts. So you can write an Aztec smart contract which has private functions, and each private function is compiled into a SNARK circuit. This has a substantial consequence when it comes to composing a transaction, because if I want to call a smart contract that calls other smart contracts, that call other smart contracts, then you have a lot of different independent SNARK circuits that are being created by untrusted actors, which means you can't effectively compose them all into a single circuit, or, for example, like run them through a single virtual machine. They need to be executed in isolation, and this requires recursion, and it requires a lot of recursion.
Just saying that some VMs do support it, like Cairo, but you can go on.
Yes, but do you support it where I need to look into the architecture, but I think with privacy it becomes substantially more complicated. Where if you have
with privacy it's more complicated. That's true.
And typically, like the way we've approached it, which I'm fairly certain a virtual machine approach would be highly problematic, would be, you have these encapsulated circuits that represent functions, and then you compose a transaction by recursively validating proofs of individual circuits and performing some kind of state transition function in what we call a kernel circuit. We borrow the nomenclature from XEXI. And so the question on our minds was, how quickly can you get recursion to work? Because the faster recursion is, the more easily you can slot it in as a very basic primitive, which allows you what it gives you is composability, really, between different smart contracts. And that's really important for us. And we can't get it in a private ecosystem any other way. And so this is where KZG has a very powerful aspect to it, which FRI and other hash-based algorithms don't have, which is that it is linearly homomorphic, as in, if you commit to two polynomials and then add the commitments together, that's the same as adding two polynomials and then committing to them. And this allows for constructing random linear combinations of multiple commitments. And why is that useful? Well, that's useful because of this new whole category of high-level crypto protocols that's come out recently, folding schemes. So starting with the Nova and then Protostar and Protogalaxy. And with the latter ones, say Protogalaxy, Protostar, something which is very powerful about them is that you can take a disparate set of clock circuits. So the actual circuits descriptions are completely arbitrary, and you can fold them all together. And so instead of having to fully recurse within the Aztec architecture, so instead of having a kernel circuit that needs to verify a function proof, we can take that function circuit and fold it into some accumulator object. And the cost of doing this is effectively 1 in terms of the number of elliptic curve scalar multiplications that you need to perform within your circuit. And so,
why is it 1? Can you explain?
1. Well, it's because you with KZG, your commitments are fully succinct, as in you have a single elliptic curve point that commits to a polynomial, and therefore, if you can represent your entire SNARK circuit as a single polynomial, then folding it into an accumulator is going to require 1 scalar multiplication on that commitment. In reality, the constants for us at least is more than 1, but there are schemes where it is just 1. And so what we're comparing is within our circuit, we have a choice of either folding, where the prover cost is less than than a typical SNARK prover, and they don't have to provide an opening proof to their polynomials. And this recursive verified cost is a constant number of scalar moles versus a FRI-based scheme where you do have to fully recurse. You have to fully compute, prove, and then verify within a SNARK circuit a honk or hyperplonk proof, including the opening proofs. And in that context, KZG is a massively standout winner in terms of just the raw cost, number of constraints required to perform that type of recursion. And so for us, it was a no-brainer.
Can I say something like, so you're basically saying that okay, you still need to commit on the extra witness, so it costs the KZG commitment, but you don't need to, you pay almost nothing to verify it.
Yes, and when you're recursing or folding, the verify algorithm becomes a prover algorithm, and therefore creates constraints that you have to commit to.
Okay, where in FRI you would have to commit and do the prove the verification of the Stark algorithm.
Yeah.
Yes. Okay.
Exactly. And so for our use case, which is privacy focused, proofs are being done client side, there's a huge amount of recursion being done. We are extremely limited in the amount of memory that we have available. KZG and a streaming system that doesn't use FFTs is the natural choice, in my opinion. And yet,
the ballpark of how many gates or constraints are required to do the recursive verification, even with the sort of aggregation or folding?
So we're still doing the benchmarks. So we've implemented it at the end of last year. It's a bit complicated because we use this protocol called Goblin Plonk to remove. So scalar multiplications within a circuit are very painful because they're non-native. So you have to emulate a larger prime field, like a different prime field within your circuit. We get around this by this Goblin Plonk protocol, but it does make measuring a little bit difficult. My back of the envelope math said it would be like roughly 8,000, 10,000 constraints. We're not quite there yet in terms of the code, but the code's not optimized. So, depending on the progress there, we may be eating our words, but I'm hopeful we can get down to those kinds of costs.
Yeah, that's exciting. I mean, I do recall benchmarking the maybe original version of Berettenberg with Aztec Connect, which was doing not using a cycle of curves and was just sort of directly verifying. And I recall the recursion overhead being something like 1 million constraints, or the recursive circuit couldn't.
It was 800,000. We got it down to 260,000, but yeah, that if you have to brute force the scalar multiplications, it's horrible.
Right.
Yeah, so a curve cycle really is necessary to make it fast.
I mean, I do want to say that on the Stark side, Plonky 2 achieved a recursive circuit with, I think, something like 2 to the 14 constraints, or maybe even less. And the sort of key, on the one hand, you don't have homomorphic commitments and you can't do any folding or aggregation. So that's true. But on the other hand, you don't need to do really any non-native arithmetic if you're using an arithmetization-oriented hash function like Poseidon, which is what they do. So that is, a distinct benefit, that you don't need cycles of curves or anything, and you can sort of directly verify a Stark proof recursively with only native field arithmetic.
Yeah, it does. It's certainly the complexity, the algorithmic complexity of doing recursion with elliptic curves is higher, because you have to use these curve cycles, and then if you want to avoid doing non-native arithmetic altogether, then it's not just curve cycles like Halo 2. You've got to use some accumulation scheme, or like some computation delegation scheme like Goblin Plonk, of which there's only one implementation, and that's ours. With regards to Plonky 2 recursion, yes, they did have very impressive numbers. I do recall that it wasn't quite apples to apples though, because the commitments aren't constant sized. I believe like the Plonky 2 benchmark was a circuit that recursed, and that's all it did. And if you actually wanted to add in like a lot of extra additional logic and constraints around that, then the numbers don't look so good. But I could be wrong with that, but I'm fairly confident that in a production system you're not going to get.
I wanna reserve time for Mamy and then also for Jim, so we can.
During my time, I can pull up a chart of some of the profiling we did on ZKEVM, which shows the breakdown of the recursive circuits versus sort of the base computation circuits.
But maybe first let's because we're still on the KZG side, so maybe we can hear from Mamy. What's your perspective on?
So yeah, I think like everyone wants to improve provers because that's costly. We need to rent big AWS instances, these kind of things. But in the context of blockchain, what's most costly is state. And as Zach said, the very nice thing about KZG, similar to BLS signatures, it's that they're very, very short. Like, and if you look into how to plug layer 2s on Ethereum, whether they use STARK or SNARKs, in the end, they have to use pairings for verification. with proof composition. So risk zero, for example, does STARK on baby bear, and then they offload that to a growth 16 prover. So we frame this as KZG versus FRI. I assume it's a marketing department at StarkWare that did this, but ultimately they kind of work together. Yeah, and disclaimer from Taiko, we're not a KZG only shop. We actually do multi-proof, so we have both Stark and SNARK based prover in our testnet at the moment.
Yeah, I think it makes a lot of sense doing this composition. Like, a lot of people are doing it right now. It's the new trend.
Well, it's also because one of the big challenge in Ethereum is we want people to be able to run nodes. I speak as an ex-Ethereum core dev. Like, I've been working on the merge for 5 years before working on ZK. So we want people to run nodes on small machines. So in the past, people tried to run on Raspberry Pi. I think they all stopped, but and this means they need to verify proof. And in KZG, you know that the verification will be the same, whatever is the size of what you verify, which is not true for Stark, though. I think if you can recurse more and more, well, I don't know about this, so I won't say something wrong. Yeah.
What is your question regarding recursing more and more?
Like, what's the cost of the verifier? Does it depend on the number of points, on the number of words that you need to verify?
I mean, if it's under a big recursion tree, then no, it doesn't depend on all the leaves.
Okay.
In the end, you just get maybe a hash that maybe has all the public inputs. This
Okay.
you need to open, but the proof itself, the verification doesn't depend on the entire recursion tree.
So it's O1 also.
I have a problem with the O of 1 thing because one has to be just, generally speaking, you know, the universe is O of 1 and we live O of 1. So like one has to be very, very clear as to what exactly is I mean, just to explain to the audience, when you say O notation, you essentially mean there's a parameter that goes to infinity. If it doesn't go to infinity, then everything is O of 1, right? Even a function, you know, 2 to the 2 to the 2 to the power 100 is a constant, okay? So if you say something is O of 1, you mean there's a parameter n that goes to infinity. So please specify what n is. And you want to say, even as n goes to infinity, something is O of 1. And I mean, I think the first place where I saw this and I didn't like it was with the very first SNARKs, where it was O of 1. The meaning there was, it was true. It said, if you're using a group and you're assuming the group has enough security, then it's a constant number of group elements. But however, practically speaking, you know, if you think of something going to infinity, you know, like security parameter or something like that, your group size there needs to go to infinity. And this O of 1 isn't really O of 1, it's polylog so. But from then, like the O of 1 became, and now more recently, linear time also became things where linear time is very murky. So I sort of, I know that everyone wants to say that their stuff is O of 1, but if you're talking about concrete things, then measurements and actual numbers are what matter. And if you're talking about asymptotic things, then you need to at least define what is O of 1 as what parameter goes to infinity. Which I think is a less interesting discussion in the context of, you know, practical, concrete implementation.
Sorry to interrupt. I just want to say I really know how to wind DLA up now because Aztec uses a linear time prover, and I will not elaborate further because
linear and what linear? You probably mean linear number of operations in some group. which is already
If
not
you
exactly linear,
conveniently
but
ignore
that's
the security
fine.
parameter, it's
What?
linear time. If you conveniently ignore the security parameter, it's linear time.
Yeah, but okay, so here, a Stark is linear time. It's linear time if you allow polylog in the security parameter. Why? Because the security parameter is always at least log n, and if you allow polylog n, then it's linear time. So if we are in the world where linear time but for security parameter, then any system that is quasi-linear is linear time.
Yeah, I mean, let's actually try and hone this down, because we use these terms a lot in a colloquial sense, where we have circuits. Those circuits have a certain number of constraints, and that number is pretty well bounded within a range. Right, it's going to be between 128 and 2 to the 24, 2 to the 25. And so we have previous systems where the question is, as that number n scales, what happens? And that's where I think it is fair to say, under those, in that narrow window, previous systems can be linear time, or they can be n log n. And in that case, I would say StarkS or anything that uses FFTs is n
not
log n.
really, because in that window, log n is between 22 and 24. So it's just a constant. If you're looking at that range, take the...
Oh, no, I said 128 to 2 to the 24. So
never mind.
7.
So 2 to the 20. Okay, the upper bound on log n for that number is 24. But even if you go to 2 to the 128 or 2 to the 256, log of that is just 256. So it's still a constant, which is why I'm saying if we're in the concrete complexity, which is extremely important, it's, these days it's all I care about, then you want to measure concrete things, and then it's perfectly fine. But talking about linear as opposed to asymptotic, it's somewhat interesting, but you need then to talk about, if you talk about linear or O of 1, you need to be in a setting where you assume n goes to infinity. You can't, as a mathematician, I'll say, you can't say something is linear, but in the range up to some number. You have to be saying, let n go to infinity. So let it be 2 to the power Google. What happens to your complexity parameter? If it stays linear as n goes to infinity, that's fine, that's linear. But if you mean in a small range it is linear, then the mathematician in me has an issue with that.
As much as I want to argue with you, Eli, I actually do agree with you here. I think asymptotics, that's something for papers and for ePrints and for Eurocrypt. Concrete costs are the things that matter. And something which is n log n, it might turn into an annoying constant, and something which is linear might turn into a not annoying constant.
Yeah, exactly. Now I love both. I actually think that asymptotics matter a lot, and I think papers that show, let's say, linear or shave a factor asymptotically are amazing things. It's just you have to pick which context, and they're both fine.
So I have some. I used to do deep learning implementations in the past. And one thing regarding those big O notation is that matrix multiplications is n cube, n being the length of the matrix. There are algorithms that are theoretically faster, asymptotically faster, called Strassen. And it's 2 to the power, 2.70 something.
Yeah.
But in practice, they are slower because of memory bandwidth issue, cache issues, etc. on computers. So I do agree that practicality is important, but between n and n log n, there is, first it's a guide. If you see something n square, you know that you're on the wrong path. If you see n log n, there is something to dive into, and we need to measure concretely what's happening. It's a guide.
Let's move to Jim. Yeah, Jim.
To briefly address this, very much on the side of we are an engineering team, we look at concrete implementation. Where these constants come from, this range, I think that Zach is talking about on the size of a circuit. On the one hand, we look at circuits that are lower bounded by the recursion overhead, which is, at least 2 to the 12, 2 to the 13, and on the upper bound, you're probably going to be bottlenecked by memory, and also where your recursion overhead is so low that it becomes negligible. So that really does put you in a range.
What's the upper bound, by the way, where you put it? 30 or 2 to the 40? Where does it end?
I guess that depends on what size of element you're committing to. I mean, I would look, memory requirements should be less than 64 gigabytes. Like, I'd like that. Right now we're at 512 gigs of RAM. That's like really expensive. So how much time do I have? I have a few things to address.
Well, I don't know, 10 minutes?
Okay, sounds great. So let me actually start with
Binius, right? You have a completely different commitment scheme. Tell us about it.
We do. I actually need to start with Polygon, though, because this really motivates the concrete recursion story. So this is a diagram from
Can
Polygon.
you zoom in a bit, please? It's very small.
Certainly. Is that big enough?
It's better.
Okay. I'm not sure. This is a diagram from Polygon showing the architecture of the ZK EVM. The main thing to know is they heavily use recursion, where you have a batch proof, which is your ZK EVM proof, which is actually a composition of many different constraints that are sort of referencing each other via lookup tables, I believe is the architecture that Zach was referring to. And then you have a sequence of recursive provers. And then this diagram shows that 80% of the time is spent in the base layer to compress the proof. So the amount of time to do the first layer of recursion to recursively compress the biggest proof is about 10% of the, close 10% of the time to do the base layer proof. So this sort of guides us towards, we really care about making the base layer proof really efficient, and we can throw some layers of recursion on top to compress these. As far as how these operations break down, is this, I need to share like a different tab here. This is weird. Sorry for the, let me do this. So again, this really, I'm talking about this because this motivated our work on Binius, and I'll get to the point very shortly. But the major computations that we found in profiling ZK-EVM, the number one is Merkle hashing, because they use a slow hash function, which is Poseidon. The NTTs are sort of this notorious bottleneck. And then you have other operations like polynomial composition and FRI batching, which are multiplications of field elements, but they're not just multiplications of your small field elements, they're multiplications of extension field elements. So you're actually multiplying field elements that are at least 128 bits. Working memory is about 512 gigs, which is just expensive. It's not something that a consumer hardware is going to have. And then the other thing we noticed is that in practice, when you're arithmetizing real computation, like recursively verifying the Ethereum enshrined hash function, you're often committing to low-valued elements, like 1-bit elements. So in Starkey's Ketchak circuit, the vast majority of data that they're committing to are 64-bit elements that contain 1 bit of useful information. So all of that led us to investigate binary fields, which are actually very much pioneered in the SNARK space by Eli, and so we thank him for all of the contributions. We benchmarked various polynomial commitment schemes here at when you are committing to different bit widths, which we find useful. This is all single-threaded, and basically Hyrax, which is an elliptic curve commitment that just allows some more parallelism, but is fairly similar in terms of the commitment phase to KZG, is just dramatically slower than all of these small field FRI commitments. And Binius, this is a CPU implementation using some Intel vector instructions, is equivalently fast to Goldilocks FRI, which is a very optimized Stark implementation over a small field when committing to 32-bit elements, and is dramatically faster when you're committing to 1-bit elements. And the main property that we're able to achieve with our commitment scheme is that the cost of committing scales basically linearly in the amount of information that you're committing to, which is huge. So we can commit a polynomial of 2 to the 28 1-bit coefficients in about half a second on a single thread using Binius with a actually somewhat recursion-friendly hash function, which is a standard hash function which is natively defined over binary fields. So we have some CPU benchmarks. We could talk about that, but the real story here is we are a hardware engineering team. Well, we're a cryptographic acceleration team. We have a kick-ass hardware engineering team, and we prototype these systems in FPGAs. In native digital logic, binary fields are dramatically more efficient than prime fields because addition and multiplication are carryless. So this is probably not the way that we're all used to thinking about efficiency, but when you're talking about digital logic, you care about two things. You care about the silicon area, or the number of gates it takes to do a computation, and you care about the propagation delay, which is how quickly can you run your clock? How fast can you clock the hardware? So we see that for the Mersenne 31-bit field, which is perhaps the most efficient field in terms of field arithmetic that would be Stark friendly in some sense. We're about 5 times more efficient in this metric of area times propagation delay for a 32-bit binary tower field. If you take that down to 16 bits, which we're actually able to use in the Reed-Solomon encoding phase of our commitment scheme, you get another, 5x improvement over that. This is, so now let's talk about how that looks for a larger type of computation, like an NTT. I think really the column to focus on here would be gate count. The way to think about this is that we are able to sustain a throughput of committing a certain throughput of information, which is 512 bits per cycle at 250 megahertz, or 128 gigabits per second. And this is the number of gates required to do an NTT at that throughput. And it's about 10 times better, or maybe 8 times better with a 2 to the 16 size Reed-Solomon code, and it's 3 or so times better with a Reed-Solomon code that is over the 32-bit field. And the real kicker is when you take into account the hash functions. So as I said at the beginning, the slowest part of Polygon ZK-EVM is running the Poseidon hash. I have the CPU benchmarks actually, but essentially Poseidon is something like 10 times slower than a CPU-friendly hash function like Ketchak or Grostel. Grostel is a hash function that's based on AES, and actually in an observation made in the original Stark paper, AES is fairly arithmetization friendly in the binary field context. So that is our selection for now of hash function to use in the Binius system. It's just a dramatically more efficient thing to synthesize in hardware, and we've done all this prototyping on FPGAs. So I think there's a lot of numbers here. I'm happy to explain more of them, but I think that's essentially our case for Binius, which is not only can you more efficiently commit to small valued elements, which it's a very useful thing to do in real ZK circuits, you can use a more efficient hash function and still get efficient arithmetization of that. And in native hardware and digital logic, all of the operations are more efficient and can run at a higher clock frequency. Yeah.
One comment on the KZG. If you can go back on the slide with the figures, because
you mean the
again
no.
before slide, not on FPGA, the slide on the yeah, 2 slides after. One, yeah, just the one just before. Yeah. So we did a review. Well, that was a year ago, but the link is in the chat. Basically, one of the issue we have 2 ways of implementing KZG. Either we actually do the bit-based KZG with lots of 1-bit elements, which is extremely slow when you use KZG, or you can use lookups with hopefully the lasso lookup singularity. The hierarchy, the first line is one that uses lookups.
I'm sorry. These are just polynomial commitments, so they're not a ZK circuit that's verifying.
Not an arithmetization of a KZG.
Okay.
So what I'm saying, the KZG on line 3 means it's a FRI polynomial commitment scheme using KZG for the Merkle tree.
Okay.
But I had a question. Okay, when you counted the number of the area on the FPGA to do Mersenne 31 computation versus the binary field, it was about 3 times the number of the area, like 12,000 to 4,000. I wonder why it's not 2 times. Like if maybe it's small detail, but I imagine that if you just neglect carries, like this is the difference if you have carries or not. So it sounds to me like it should be like at most 2 times. Why is it?
I don't have an intuition. I know that like I'm happy to connect you with our hardware team who can give you a more detailed view. I mean, what I can say is that we can implement all of the binary field operations using only lookup tables. So the resources available in an FPGA, well, there's several, but among the main ones are lookup tables and these DSP digital signal processing units that are basically small multipliers. And we don't need any of those for the binary fields. And they,
I see. It makes sense.
Produce an ASIC, it's a lot more, logic to implement those carry like integer multiplications.
Gentlemen, I think we need to start wrapping it up. One question, and then maybe a quick round of where do you stand, or which commitment scheme is best, or which ones do you use? Is that okay? So there's one question. I guess it's for you, Shahar. How are the parameters being set with respect to security for FRI by Kev?
I mean, it depends on who sets them. With StarkWare, I think we are not using, for example, the provable parameters. We are doing the more practical parameters. It affects mostly the verification part, so not the proving. The parameters we have for the proving is a blob factor. We want it. It's a trade-off between the prover and verifier, but like Jim showed, that we really want to make the leaves as efficient as possible, and the recursion probably be a lot less. So we are tending towards choosing a small blob factor. Are there any other parameters that I need to think about? I don't think so.
At some point, there's you need to take an extension that's large enough to get security. If you work over a 30-bit field, you probably need a degree 4 extension, which would bring you to 128 bits.
Yes, this is not in the
commitment phase.
Right. Yeah. Exactly.
So let's do a quick round. Any parting thoughts on which is your favorite commitment scheme? I'll stay out of it. I mean, I have my favorite, but I'll let you guess.
I want to say that my conclusion is which commitment scheme is better is it depends. Depends on seems like if you want raw speed on FPGA, it's a binary field one. Maybe I think that applications like GPU fast, maybe larger servers, and then FRI is very good. Maybe if you want on mobile end devices and you need ZK and the recursive things, maybe KZG relevant, or for the last part of the proof that goes on chain, KZG based. So it depends. That is my conclusion.
Who's going next?
I guess I can go next. Well, as I said, at Taiko, we are using both because we want to have independent proof systems so that if something happens, just like Nova on a cycle of elliptic curve, we aren't totally broken and we can rely on the other, like we use both STARK and SNARK. Now, for a bit of fun take, I must say that the KZG-based proof has a better marketing because you have Nova, Supernova, Hypernova, you have Protostar, Protogalaxy, you have Kilonova now. I mean, it's just way better marketing-wise.
I completely agree with that. Definitely much better marketing.
FRI is a weak name. You need Super Fry or Mega Fry.
Well, there's Deep Fry. There's Deep Fry. There's Deep Fry. It's deep.
Yeah. It's not Galaxy Fry though, is it?
Yeah, you're right. You're right.
I mean, we're very excited about the binary field work. Agreed that a lot needs to be figured out. There's a lot of sort of research features to add. So the main one is for privacy preserving use cases. We have not proven a zero knowledge secure variant of our binary field commitment schemes. This seems entirely possible, but requires work. And then we, are designing a proof system right now with very large proofs that would need recursive compression to become practical. So, but in terms of just raw computational efficiency, that's where we're looking. And even on CPUs, we think the advantage of efficient arithmetization of bitwise operations just adds, a lot of weight to that approach.
So I remember asking your team a month ago about more benchmark. Ideally, I would like to benchmark KZG on my CPUs just to have to do through Binius so that I can compare with other commitment schemes.
Yes, you're saying you want to benchmark a Binius proof of the KZG.
Yeah.
Yeah, we are actively working on that. Should have hopefully in a month that will be live in our open source repo. You can follow the progress. We're developing an open source Rust implementation. So as soon as that's available, you will find out about it.
Zach, your turn, and then there's a question we'll answer that came. But Zach, so what's your favorite?
Sure. So I mean, if I was going to give the the safe answer, I would agree with Shahar. I think it's very level-headed. However, I'm going to give the salty, spicy answer, which is that I think the future is going to be ZK. As in, if you think about your typical interactions that a user has with the internet, it's not just going to be it's all going to be mediated through ZK, SNARK, and zero knowledge proofs of correctness. And those, where you need privacy, you care about succinctness, you care about you have garbage tier levels of memory and resources to work with. They're going to be using some check protocols, and they're going to be using KZG. That's my claim. You can at me on Twitter in 5 years and call me out on that if that's not true. You can, but you don't have that linear homomorphism, which means you don't get that high quality recursion that you're going to really need if you want to create composable systems out of zero knowledge protocols that are written by multiple different actors.
Well, I think you can do it with FRI as well. I don't understand all the details of what you said, but
No,
It seems like I'm the only one that gave the politically correct answer.
It's composability. I'm sorry, yeah, I'm slandering you, Shahar. But it's about this, like, okay, so composability is an overused buzzword, but it's used for a reason, right? Imagine I'm running some rinky-dink web service and I want to interact with some other service, and I do that through a zero-knowledge proof. So I send them a zero-knowledge proof. And then that web service wants to interact with some weird social media app which also mediates through the medium of zero-knowledge proofs. And in order to kind of to perform basically like almost like a data transformation pipeline from the information I got from my clients, you're going to need to use some level of recursion to compose those proofs together. And that's kind of what I mean by like written by different actors. As in, yeah, you can do it with FRI, but recursion is slower in FRI. And the amount of information being transmitted is more, and the amount of memory that gets consumed is higher. And those are all really, 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 really important when you're making proofs on a potato.
I want to pause you here just because, first of all, so we're going to talk again in 5 years and see what's happening. I'll actually put a calendar invite to all of us for 5 years out. Now you can do it. Let's just answer this last question that I see arose by Bartek. Let me see. So, when doing FRI, some protocols go down to single value, but some stop at, let's say, 128 last degree bound. My question is why there is the different approaches to this. Is going down to single value safe in the context of precipitate gap research? Is it just about optimization? I understand some of the words, but not all of them. Shahar, maybe you can understand.
It's just, it's easier to not do this optimization. The optimization is better in practice. I mean, there's no reason not to do this optimization.
Oh, I think I understand. Like when you do FRI layers, do you stop at a single value or do you stop at a polynomial? Okay, got you. Yeah, it actually improves a little bit soundness because the less layers you do, you get something that is safer, but then you send more information. So it's actually more sound, but more information. Okay, so we're going to meet again in 5 years to discuss the status of. No one will talk anymore about KZG or FRI or Binius, right? It'll be well, marketing is going to do its thing, so it'll be black holes and I don't know what else, and super galaxy, whatever is. So quarks. See you all in 5 years, and thank you, the audience. We'll meet again at our next Stark at Home, which will probably be about economics next time. Okay.
Thanks
for the invite. It's been a pleasure. Cheers.
Bye. Thank you all.